All right, so for a material in which every plane is a plane of symmetry, we call that, what do we call that? Isotropic material. And so for that material, then our generalized Hooke's law, I'm just going to write it out again. Lambda plus 2 mu, lambda, 0, 0. I'll talk about what these lambdas are in a second, lambdas and mu's. Yes.
That matrix is 3, 1, right? Sigma, 3, 1.
Yeah, you have 2 sigma, 2, 3.
Yeah. Thank you. So lambda is known as Lemay's constant, but it's related to other elastic constants that you may be familiar with. So for example, mu is the shear modulus, nu is the Poisson ratio. So if you knew the, basically when you're talking about isotropic elasticity, there's various material constants that we can use, but they're all related. If you know 2 of them, you can figure out the other one, like the one you were looking for. And we just write them in certain ways so that the equations become more compact. We'll see that in a second. But otherwise, so for example, if you knew the shear modulus and the Young's modulus, then Lemay's constant is that. If you knew the bulk modulus and the shear modulus, bulk modulus K, then you have that relationship. So I'll just write out what all these are, right? So Lemay's constant, we'll talk about that as last, because the other ones have better physical interpretations. So K is a bulk modulus. The bulk modulus is a measure of a material's resistance to volume change, right? So the way we physically measure that in the laboratory would be you'd basically go in with a cube and compress it equally on all sides, apply an equal force to all sides, and then measure essentially the change in volumetric, the change in volume, right? And so essentially the change in stress over the change in volume would give you the bulk modulus, right? E is the Young's modulus, or the elastic modulus. Sometimes it's just called the elastic modulus. So for the elastic modulus, it is a measure of a material's resistance to a uniaxial deformation, right? So you typically measure Young's modulus. You go to the lab and you pull on something in a uniaxial way, and you measure the strain, right? The axial strain, and you measure the axial stress, or really the force divided by the area, right? And so that gives you the Young's modulus. It's the change with respect to the uniaxial deformation. Mu, and sometimes in the literature and elsewhere you'll also see most of these symbols are fairly common, like K is almost always the bulk modulus, E is almost always Young's modulus, lambda is always the Lemai's constant. The one that's different is mu is sometimes, it's used as the shear modulus, and sometimes G is used as the shear modulus. And, I don't really know why, perhaps because just in fluid mechanics, sometimes you have a shear viscosity, or like a viscosity, and you use like a mu for that term, right? So, I don't know. Sometimes it's G, sometimes it's mu. But this is the shear modulus. So this is material's resistance to shape change, right? So typically don't do this type of experiment, but if you did, if you could imagine like some setup where you deform, you take your initial sample and you deform it in a way that preserves the volume, right? So you don't change the volume in any way, but you just shear it, and then measured the loads in such a way that you could, get the shear modulus. Again, typically don't measure it like that. It's inferred from other things that are easier to measure, right? Elastic modulus is easy to measure, really easy. It's the most common, right? The bulk modulus is, if you have a triaxial confinement system, you can measure it directly. It's not that hard, but a little bit harder. The most common kind of secondary measurement is the Poisson ratio. So, who knows what that is? Yeah, that's how you'd measure it. That's exactly how you measure it. So what he was saying is you can go to the lab and you can you can actually measure Young's modulus and Poisson ratio in the exact same test by placing two strain gauges. So if you have a strain gauge that's oriented this way vertically and one that's oriented horizontally, then the ratio of those two strains would give you the Poisson ratio. Right? So it's a measure of how much. So like when you typically you do a tensile test on the metal, right? You're going to pull on it, it's going to get longer. It's also going to get narrower, and it's that ratio of elongation to narrowing. That's the Poisson ratio, right? Poisson effect. Okay. So those are the two. Again, because of the ease of measuring them, the ones that you're typically directly measured would be the Young's modulus and the Poisson ratio. And then once you have those, you can get all the rest of them, right? And again, if you just go to Wikipedia or you Google like table of elastic constants, it'll show you a big table, and you can basically it gives you the option if you know two parameters, it'll give you the equation for any other parameters that you want. Right? So again, if you know two of them, you can rewrite these equations to get any of the other ones. Right?
What is
Yep.
the value? Poisson's ratio's value? I mean, the highest value is 0.5.
Yeah.
What is it, sir?
So, that's a good question. So when you have a Poisson ratio of 1/2, the material is said to be incompressible.
Yeah.
Okay, and if you were to go and write, I don't have the equation in front of me, but if you were to write down like whatever the equation is for K as a function of Poisson ratio and any other constant, if you put in a value of 0.5 there, for whatever that equation is, if you put in a value of 0.5 for Poisson ratio, not shear modulus, sorry. So if Poisson ratio equals 0.5, then K is infinity. So yeah, so the material is said to be incompressible because the bulk modulus goes to infinity when you have a Poisson ratio of 1/2, according to this theory. So that means that you can't change, K is a measure of the material's resistance to volume change. That means you can't change the volume at all, right? If the bulk modulus is infinity, it would be impossible to change it, right? So that's why, it's always in the range of 0 to 1/2. If it were negative, like that would be an interesting material. And there's like a lot of, nowadays there's a lot of research done in what are called like metamaterials, where, nowadays with special lithography techniques and other, deposition techniques, at a very small scale, you can control, like what I'm talking about, small scale, like things you can only see with electron microscope, right? You can control the architecture of a material in such a way that they can have interesting properties, right? And one of the sort of holy grail material properties would be a material that had a negative Poisson ratio. And what that would mean is that, if you I used to work in like a lot of ballistic stuff, and so if you had a material that had a negative Poisson ratio, it would make a perfect bulletproof vest, or a really good bulletproof vest, because what that would mean is like if a bullet hit it, the material would contract on itself and like become more dense. So there are materials like these so-called metamaterials being developed that have those kind of material properties, right? One interesting, there's a lady at Caltech, her name is Julia Greer. She's got some pretty cool videos on YouTube. She builds these nanostructures out of like single layer of silica, right? So essentially they're ceramics, right? And if you know anything about a ceramic, you know that ceramics are really hard, right? They're really hard, but they're also very brittle, okay? They're brittle because they have defects, kind of just like rocks, right? You can't make a rock without defects. Nature doesn't make rocks without defects. You can't make large-scale ceramic structures without defects. But at the nano scale, she can make materials that are basically single layer of ceramic, and so they're incredibly strong, and they don't have any defects because they're just a single layer, right? Now, and so you can build up a material, and the biggest one. This is a few years ago when I talked to her about it, so maybe they're more advanced now. The biggest ones that they can build, are maybe like a millimeter thick, and maybe like a centimeter square. But like that's something you can hold in your hand, right? And the thing is, like you can barely see it. It kind of looks like dust in your hand, and yet it has material properties that are stronger than steel. So like what could you do with this? You could, for example, make a lighter than air vehicle by vacuum. Like if you can make a structure out of, like a closed structure out of these things, right? This little nano architected materials, you could draw a vacuum on it. A vacuum is lighter than air, and the material is so light that you potentially could have a lighter than air vehicle without like having helium or some, like thing like that. Because we're running out of helium. The Earth is running out of, every time you release helium, it just goes into space. So we're running out of helium. So you can make kids balloons, I guess, out of these nano architecture. But the problem is, it's interesting, but like how do you scale that up to make something of it? Like you could actually engineer a structure, right? But anyway, that's like nano architected materials is like an active area of research. And
But mathematically, why
So that makes the Poisson ratio 1, right?
The radial strain. I mean, I see your question. Like, if you just went to the lab and you measured that, like, you're like, well, that's what it tells me, right? But I think that the reality is that it's in the material properties that anything once you get to a half, the bulk modulus goes to infinity, and you just can't. It's impossible to strain it anymore. Yeah. So you would just never observe anything. In reality, you'd never observe anything like that, right? So, yeah. I think that's the answer, yeah. So, soon we're going to learn about plasticity. I guess we'll probably get to it in the next class at this point. We'll learn about plasticity, and particularly in metals plasticity, we assume that the plastic behavior is isochoric, or in other words, that's just a fancy word for volume preserving. So in metals, because the way a metal deforms plastically, right? So now we're talking about like a paper clip again, right? If you bend the paper clip, if you just pluck it, it goes back to its original shape. But if you bend it too far, it stays there, right? So the way like that actually occurs in the microstructure is like there's crystallographic planes, and they slip over one another, right? And that's always through shear deformation, right? And it's pretty well experimentally verified that like plasticity in metals is isochoric. It's volume preserving, which means also the Poisson ratio during plastic deformation is 1/2, right? So you have an incompressible material during plastic deformation in a metal, right? And we're going to learn about metal plasticity first, because you got to crawl before you can walk. but then we're going to go on to geomaterials. Geomaterials, because they have pores in them, you can crush the pores out, and so you can have like a pressure dependent or non-isochoric plastic deformation in a geomaterial. So let's see. Okay, got a little bit more to say about this. So for isotropic materials, then returning to tensor notation,Cijkl is equal to lambda, the Kronecker delta function, Ij, delta Kl plus mu Ij Kl plus Il Jk. And so if we put that into our generalized Hooke's law, sigma Ij equals Cijkl epsilon Kl, right? So I'm just going to substitute that in. And then let's just look at like what happens. So we have epsilon KL, and it's going to distribute across those terms, right? So let's just we're going to look at like how this changes or contracts with these Kronecker delta functions. So I'm just going to look at this one term, but the same thing would happen over there. So we have IL JK epsilon KL. So remember when we first talked about this, if you have a Kronecker delta function and you have a repeated indice, right? So in this case, right, like our L's are repeated right here, then I can pass over. We can do it either way. I guess we'll talk about the K first, right? So I have a K and a K, so those are repeated indices. So when I have something times a Kronecker delta function with a repeated indice, basically I can replace the K's with the J, right? So like the two K's I can replace with the J. So then I get IL epsilon JL, right? And then I can do it again so that ultimately I get epsilon JI, right? But our strain tensor is symmetric, so we could also write that as IJ. Okay. So if you pass that over, if you follow those same rules across the whole thing, then we get so that is generalized Hooke's law for an isotropic material in tensor notation. So that's epsilon KK. Just to clear that up. K, right? So that's, anytime you have a repeated indice, right, you can replace it with anything. So that would be epsilon II, KK, JJ, right? But basically that's the trace of the strain tensor, right? So, yeah, so this is kind of where Lemay's constant comes in. It doesn't really have a physical interpretation, but it allows you to write this equation compactly, right? And so if you substitute any other constant, meaningful constant in there, then you're going to have like some bigger coefficient up front, like it's a function of Young's modulus and Poisson ratio or whatever. Right? Just real quick, one last thing. If we let J equal to I, so then we write out everything. We have sigma I equals so if I understand, if I let I equal to J, then I have I here, right? But it's a dummy indice, right? Anytime you have a repeated indice, it's a dummy indice, and you can replace it with anything, right? So I could say I could say JJ, I could say KK, right? It's going to give me the same thing. So if I do that, if I write KK here, right? This thing, this is the trace of the identity matrix, right? What is that equal to? 3. Right? So delta II is just 3. And so then I get sigma, KK equal to 3 lambda plus 2 mu KK, or that leads to, I can invert it, so epsilon KK is equal to sigma KK 3 lambda plus 2 mu. And if I take this, substitute it in there, then that allows me to invert this equation in terms of strain. So if I wanted to write the strain in terms of stress, and here it's more convenient just again because of compactness to change the parameters to use Poisson ratio and Young's modulus. And, there, you're just making the substitutions that So yeah, if you take this and substitute it in there, and then you substitute in these two relationships for the lim A parameter and the shear modulus, then everything reduces compactly to this equation here. So, generalized Hooke's law for isotropic elasticity. Just in the interest of time in this class, I'm only covering like the full 3D version of the equations. But I think briefly one lecture I just mentioned plane strain and plane stress, right? So that allows you to collapse the 3D equations to 2D, and it really just depends on the assumption, right? Plane stress would be a situation where you have a material that is long and slender and thin, such that you're not worried about the change in the stress through the thickness. You assume it's the same, right? That would be a scenario of plane stress. And then plane strain would be like a very thick section, such that you're assuming that the strain through the thickness is very, very small, right? Such that it's approximated by 0. And so in those two scenarios, you can reduce these equations even further. Any book on elasticity. And I mention that because sometimes it's useful to solve problems in 2 dimensions, right? Like just solve a 2D finite element analysis is easier than solving a 3D one, right? So, so sometimes it's useful to do that, and you can reduce these equations to plane strain or plane stress and then solve 2D problems. But with the understanding that, it's a 2D problem, but the fact that there is some through thickness information is included in there, right? In the interest of time, I'm skipping all the equations for that, but just know that they're out there. If your problem of interest, it can be well approximated as plane stress or plane strain, you can implement it in 2D using those 2D equations, which are just reductions of these more general equations. Okay? I think that's a good place to stop for, I think that's a good place to stop for today. I had some figures pulled up, but I think they're more related to plasticity, which we'll talk about next time. All right?